there, and welcome to Lab 6. So this lab is going to be a little bit different from the other labs. It's going to be a lot less hands-on practical work and a lot more of kind of me talking at you guys, more lecture and demonstration style stuff. So what we're working on here is largely lab practices, in-person electrical engineering lab practices. Obviously, you guys can't do these right now. Which is why we're going to prepare this little video in the hopes that later at the end of the semester or in future classes you will have the opportunity to work in an electrical engineering lab. All right, so first of all, this is the lab that we usually do work in for this class for 2210. This is, I believe it's room 2275 in the Merrill Engineering Building. Number's not super important. A lot of the labs look like this. And I can kind of show, I don't know, there's not a lot of interesting stuff in here. At least not from the back corner where I am right now. But this room is full of little lab spaces. Each is a workbench. We have a PC. We have our equipment here that I'll get into in a little bit. Yeah. And you've got all the wires, and there's a door to the stock room right there. So you have all the equipment that you could need right here. All right, so the first thing I'm going to go over is some basic lab safety. Because, you are working with electricity in labs, it can be dangerous. And we want to make sure that you're protected and that all of your equipment is protected as well. All right. So, very first thing is in labs, you really should not bring any food or drink. Some water is okay as long as, you keep it far from your circuit and any electronics, and you keep it in a sealed water bottle. Other drinks and food we generally don't like in here, largely because we just don't want to get stuff in the equipment, right? We don't want to have crumbs and sticky stuff all over here. And yeah, that's the main thing is, we just don't want to make a mess in here. We want it to stay clean and be a good lab environment for us. So that's very first thing. The second thing, I've talked about this before when I'm doing labs at home, but this is don't leave hanging sources. So what do I mean by that? Hanging sources are just going to be voltage or current sources that are not connected to anything. Their probes are just hanging. They're free in the air, right? And so I'm going to demonstrate what not to do here. So we've got this equipment stack. This bottom one here, this is our DC power supply, right? So this generates voltage. And just a quick overview of the rest of these guys. This top one, that top box there, that's our, that looks like it's a function generator. It's a sine wave generator. The middle one is a multimeter, and the bottom there is a voltage generator. I know it's hard to see a little bit through this camera. It's not the greatest for sure. Anyway, so all of these together, they form our basic lab kit. These are what we use in just about any circuit. So this bottom guy, this is what we use for DC power. So if I turn it on, it's going to go through some stuff, and I can set a voltage on it. So I'll twist this knob and I'll go in a little more in depth as to what I'm actually doing here in the next video where I'm going to discuss more about lab equipment. But for this is just lab safety. All right, so now we have 12 volts between this red probe and this black probe because that is what is being generated here. And this is not plugged into anything. So this presents a danger. Right? You could potentially, you're really not going to get shocked with 12 volts, but you could potentially. You could also accidentally bump it with a piece of your circuit or another piece of sensitive electronics, and this can cause a lot of issues. Now, power supplies here are generally pretty safe, and you'll note, actually, if I touch these two together, watch the voltage level here. It's going to drop almost immediately, right? So that is a safety measure. What that is basically it's a failsafe. This is noticing a way too high current draw because when I connect these two, I'm shorting it, right? So this is one of the dangers. And when I short it, it's going to draw way too much current, and so this is going to drop in value. Now, this is because our voltage generators here are pretty nice. They're good equipment, and they are able to have that failsafe. But you don't want to always rely on failsafes, right? So if this didn't happen, and I'm sure as anyone who ever like jumped a car or worked with electronics for a long enough time, if you touch these two together and that voltage doesn't drop, you'll get a spark, right? Because shorting equipment doesn't like being shorted, and it'll generate a spark, which can start fires, it can shock you, it can cause a lot of issues. So we want to avoid sparking for sure. So of course we have our failsafe here where it's going to detect that too high current and it's going to drop its power. On older equipment that wouldn't happen. You may blow a fuse and just break the equipment, or again you may cause a spark, which is dangerous. So what we do here, you just simply you want to turn your voltage source off, right? And so there's a little button here, I don't know if you can see it, but it says output on/off. Anytime you're unplugged, you just want to hit that, and it's going to turn your output off, right? This is a pretty simple way to deal with it, and then when you turn it on, it'll resume exactly at the voltage you were at before. Of course, you can go ahead and turn your whole voltage source off with the power button over here. The problem here is that now you have to start it up again. And so if I start it up again, it's not going to remember what I was doing, so it's going to go back to 0 volts, right? So I strongly suggest just use this output on and off button to control your voltage source here. Now, I mentioned that we also have a sine wave generator, a function generator. That's this guy up on the top. So if that guy on the bottom, that generates our DC voltages, the box up here, our function generator, this generates AC voltages, AC signals, right? So if this uses a slightly different cable than what we were using before. It uses this kind of circular coaxial cable. It's got some shielding and stuff. You don't need to worry about it too much, what's going on. But we'll plug this in here. And how this guy works, it's just one cable, but it does split at the end. So you can see that one cable splits into a red and a black, just like that. All right. And so if we turn this guy on, it's going to tell us a frequency, right? So 10 kHz. So this is generating a 10 kilohertz sine wave. You can tell it's a sine wave because of the little sine symbol. This can also do square and triangle and other waves. But again, I'll get more into this later when we talk about actual lab equipment. So this is also a voltage source, right? And so this should likewise not be left hanging. And in fact, this signal is actually more dangerous than the DC signal. So AC signals are potentially up to 3 to 5 times more dangerous than DC signals at the same current and voltage, right? So always watch out for AC signals because, yeah, they're more dangerous and they can cause a shock. They can do some harm. So I don't believe there is a way to just turn on and off our power, our output here. We may be able to. No, that doesn't seem right there. Yeah, I think we just have to shut off the whole power supply when we're dealing with this guy. There's no simple output off button like with our DC voltage generator. All right, but just make sure you are watching out with your AC voltages. You really don't want these to be hanging. They can do a lot of harm to you. So, on that same level, I want to talk about what is dangerous with electronics and with electrical engineering, like we are doing here. So, probably everyone has seen signs that say, danger, high voltage. So that's a little bit of a misnomer. Those are written that way because people respond well to them. They think of voltage as dangerous. But really the dangerous thing is current. All right, so watch out for current because current at around just 10 milliamps, that can produce a pretty decent shock, right? So that can hurt pretty bad if you have 10 milliamps running through you. At 100 milliamps, you get something really dangerous, which is called muscle contraction, right? So what happens with that at around 100 milliamps is essentially you lose control of your muscles. So if you ever touch a live wire with 100 milliamps, you can basically, your hand will tense up and contract on the wire. And what's really dangerous is that you are then unable to let go. And obviously that's going to cause problems as more and more current rushes through you. So if you ever have to touch a live wire, first of all, don't. Try and shut off the power sources before you have to touch a live wire, but do so with the back of your hand if you have to. Right? If the back of your hand, if I get that 100 milliamps through me, my muscles will contract, but I'm touching with the back of my hand, so I'm not clutching the wire here, right? And I can still pull away. So that's basic safety. We will not be working with currents that high. 100 milliamps is pretty significant, although it does sound pretty low, but we generally do not touch amperage that high. Now, as I mentioned, AC is more dangerous than DC. There's several physical reasons for that. The main reason is that as current is flowing back and forth, it's switching polarity, which causes more burning, which is the same way that microwaves work. So, of course, be very careful with AC signals, especially low frequency signals. Those are even more dangerous. All right? Okay, so yeah, remember, the main thing that you have to watch out for is current. Now, of course, I am not trying to scare you guys out of the labs at all. We will never be working with current this high. I personally I've been working in the labs for 4 years, and I have never gotten shocked. I know people do get shocked, and they're fine. It's just a little pinch, and they walk away because we don't deal with currents that are high enough to do damage here. But of course, we want to make sure that we're being safe with our equipment, right? And we're watching out for currents, we're watching out for AC signals, and we're watching out for things that could potentially do harm. All right? Now, dealing with current, one of these safety measures that we have is you want to give current a faster route to ground. So what do I mean by that? We've looked at circuits before, and as you can tell, the current is going to take the shortest path to ground. Or most of the current will take the shortest path to ground. So if you are working with highly sensitive currents and you are afraid of current going through you, you are going to want to ground yourself. Usually, you will use what's called an electrostatic discharge mat, which I can show. Let's see. Okay, so this is an electrostatic discharge mat. It's just a big mat, basically. Looks like a yoga mat. But the point is that it is connected directly to ground, and then you have this little bracelet that you can actually put on your wrist, which grounds you. So there are a couple of reasons for using this electrostatic discharge mat. First of all, as I mentioned, it gives a shorter path to ground. So if you touch a live wire, current will rush through your hand into the wrist strap and straight to the mat and to ground. That's a much safer way to discharge current. In the worst case scenario, you'll get a shock in your hand. But the dangerous thing with current is if it goes through your heart or any vital organs. That can cause a lot of damage. It can cause heart palpitations. It can do a lot of damage there. The other reason for the electrostatic discharge mat is, well, what's in the name? The electrostatic discharge part of it, which is, as I'm sure anyone has experienced, if you rub your feet on a shag carpet or you rub a balloon on your hair, you get charged with static electricity. Now, you're pretty much always charged with a little bit of static electricity, depending on the material you're on, all that. Now, electrical engineering labs, we have tiled floor. So that's going to reduce your static electricity a lot. But it is still something to consider, especially when you're working with really highly sensitive circuits. So what can happen is if you are charged with static electricity and then you go to change your circuit, you got to touch something, it can all suddenly discharge through your circuit. And that can break components, it can mess up your measurements, it can break your circuit. And so the other reason for working with one of those mats one of the electrostatic discharge mats and the ESD bracelets, sorry, ESD being short for electrostatic discharge, is that you are constantly grounded, which means that you don't have any static electricity charged up in you. It is all going to discharge straight to ground, and you know you're working on a neutral surface. So you put your circuit on that ESD mat, you wear the bracelet at all times. Sometimes they also have ankle straps, and that will keep you from gathering static electricity and potentially breaking components. Now, this guy here is wrapped in tinfoil because this is a highly sensitive component. So the tinfoil acts to discharge any static electricity around the component. It doesn't enter the component and potentially break it. I actually forgot what this is. It's just something that I've had in my lab kit for a while. I think it's an op amp of some form, but it's highly sensitive. So I'm not going to unwrap it now because I could potentially break it just by having static electricity, because I do not have an ESD mat here. So that's another thing to watch out for when you're working with highly sensitive circuits. Other than that, can you touch a circuit? That's a good question. And actually, most people will automatically assume no. And that's not actually usually correct. You can actually usually touch a circuit. And there's a couple reasons for this. So you guys have seen in lab before how if you put a really large resistor in parallel with a smaller resistor, the large resistor has virtually no effect on the circuit, right? Now, that's because, of course, the current is going to go through mostly the lower resistance part of the circuit. Now, the human body, human skin, is in the range of a couple mega ohms in terms of resistance. So that means whenever you touch a circuit, you are adding your body in parallel to that circuit, right? Because you are likely grounded. If you're touching the ground, you're touching a chair, you're grounded in some way. So if you touch a circuit, you are adding yourself in parallel, not in series. You would have to break your circuit and then connect two pieces of the circuit with your hands to be in series. It'd be very difficult to do. So you are likely in parallel with the circuit, and you'll have little to no effect on the circuit there. Now, you do have to be a little cautious as resistances approach and go above 100 kiloohms, because that is becoming within a 10 times scale of your own resistance, right? If you're 1 mega ohm, if you're working with a circuit that is 500 kiloohms, then you could actually have a pretty big effect by touching it. Now, in order to demonstrate this quality, I'm going to turn to my multimeter right here. So as you've seen before, we've used multimeters, and they can test the resistance of different resistors. So here I have I don't know if this is going to focus on it. It is a brown, black, red resistor, which should be 1,000 ohms. All right. So if I turn on my multimeter, I'm going to turn it on to detecting ohms or resistance. And now I'm just going to hold the resistor on with my hands. And look at that. We are detecting just about almost exactly 1,000 kiloohms. Now, of course, this isn't perfect because my body is going to be affecting it a bit, just making contact there. But what you'll notice is that we are reading almost the exact correct resistance, which is showing that me touching the resistor while we're doing that isn't really making a difference. Sorry, I keep bumping this microphone here. Now, if you wanted a more precise measurement, you would, of course, have to measure the resistor without touching it. Now, there's a couple ways to do this. You can stand it up in a breadboard and measure it like that. I was dumb and I forgot to bring my breadboard today, so I can't do that. But we can use some alligator clips. And let's see, so we can clip this guy right to the end of the probe that's plugged into our multimeter. And we'll clip this other alligator clip right to the black one. And so I color-coded these just to keep them straight. Of course, the colors don't actually mean anything. It's just helpful for me that all my wires are the same color. So now, using alligator clips, I can just clip them to each side of my resistor, and we can get a measurement without me touching it or interfering. And you can see, again, 0.994 kiloohms. That's just about exactly what we were getting when I was touching it, right? Now I'll touch it, and you can see I'm having little to no effect on the circuit. I bring down the resistance by a tiny, tiny bit, but it's so fractional that is well within the margin of error of this resistor. Now let's take a look at a different one. So if I get a brown, black, yellow resistor, this is a 100 kiloohm. So this guy here is 100 kiloohms. This is much closer to the resistance of the human body, and so now I'm going to have a larger effect on the circuit. So let's experiment. Let's try it out. So if I connect this, you can see we're reading 98 kiloohms, pretty close to our 100K. Now if I touch it, see now we're down to 90. So I brought that down by almost 10K ohms just by touching it. So you can see that you have to be much more careful with circuits when you're working with higher resistances, because your skin, your body, won't have such a high resistance in comparison. See, I can bring it down even further by just making more contact. The more of it I touch, the lower it'll go. Now, of course, this is a problem because it's going to throw off our measurement. But what's also dangerous is the more effect you have on a circuit, the more current is going through you. So if you were working with a high resistance circuit, you could potentially accidentally touch that and send a lot of current through you and get a pretty bad shock from that. Now, of course, typically we work with pretty low resistance circuits here. So again, you don't have to worry too much, but always be careful about touching your circuits for several reasons. You can throw them off, you can get a shock from yourself, you could cause some electrostatic discharge and break some components. There's a lot of bad things that can happen. So be careful with your circuits. Alright, I believe that was all in terms of lab safety stuff. So just as a review, no food or drink, don't leave your sources hanging, be careful with high current, especially high AC current. If you're working with a highly sensitive piece of equipment, use something like an electrostatic discharge mat to ensure you are electrically neutral. And be really careful about touching circuits when you are working with high resistance. Okay? Oh, and of course, as I mentioned with working with high current, if you have to touch something with high current, make sure you use the back of your hand for safety so that your muscles don't contract around it. All right, I believe that is all for this lab safety video. It went a little longer than I expected, but there's a lot of important stuff to cover here.